In this video, I want to do a example calculation for the work energy theorem. So we'll use a slightly different example. So let's think about a ball that's 1 kilogram. It's not moving, so initial velocity is equal to 0 meters per second. And it's 3 meters above the ground. Don't ask me how it got there, but that's where it is. And I want to know what is the velocity of the ball right before it hits the ground. And from a kind of a mechanics standpoint, this isn't actually that hard of a question to answer, right? Because we would just need to figure out the time it takes for it to fall and then multiply that by the acceleration, and that would give us the final velocity. But thinking about it in terms of energy gives us a slightly different and perhaps more powerful way to look at it. So the important thing to see here is that if we find the net work done on the ball, we'll know how much its kinetic energy changed. And we know how much kinetic energy it started with, so we'll be able to go backwards and figure out how much it ended with. Once we have the final kinetic energy, we can use that to solve for the velocity. So to get the net work done, we have to think about what forces are acting on this ball over what distances. And then the only one that really comes into play here is going to be the force of gravity, right, over this distance of 3 meters. And this is, of course, if we're ignoring air resistance, which will be okay for this example. So the net work is going to be just equal to the work done by gravity. And that's going to be the force times the distance. And then the force is going to be mass times acceleration due to gravity. So we'll have 1 kilogram times 9.81 meters per second squared. This gives us the force. We multiply that by the distance that it's applied for, which is 3 meters. And that will get us 29.43 joules. And that's going to be the net work done on the object. So we know that the change in kinetic energy must be equal to 29.43 joules. And we know that the change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy. But the ball is at rest, right? The ball is at rest when we start. So it has a kinetic energy of 0. So we have that 29.43 joules is equal to the final kinetic energy minus 0 joules. So 29.43 joules is equal to the final kinetic energy. So now let's use that to figure out the velocity of the ball right before it hits the ground. So if we have 29.43 joules is equal to the final kinetic energy, we know that the kinetic energy is equal to the 1/2 times mass times the, if this is final kinetic energy, it will be the final velocity squared. Well, let's just kind of generalize this algebraically. So if we see that Ke equals 1/2 mv squared, that means that 2 times kinetic energy equals mass times v squared, right? What did I do? I multiplied both sides by 2. And I could say that if I divide both sides by m, right, I'm left with 2 times kinetic energy over mass is equal to the velocity squared. If I take the square root of both sides, I have the square root of 2 times the kinetic energy over the mass is equal to v, velocity. Now we just got to plug it in. So for our example, we'll have the square root of 2 times 29.43 joules divided by 1 kilogram, which gives us 7.67 meters per second. Voila. And this is really helpful when we do more difficult problems where there's going to be more forces involved. And we'll do one of those next.